Hello?
That sounds great.
Sounds good, right?
Yep.
Okay. Hopefully that's not too loud. Okay.
No, I'm going to project so I don't have to switch again, but that's not going to be an issue.
Okay. Yeah, let's just put it in the pocket.
Okay, we're going to start our seminar and colloquia today. Thank you so much for coming. We have a special guest all the way from University of California, Berkeley. That's Dr. Shaosui Zhu. So Shaosui got her PhD from the University of Michigan under Mike Lamone, and she has done a lot of work on electron transport modeling at Mars. She is the deputy PI of NASA's ESCAPADE mission. That's a twin satellite in phase C going to Mars. She is also the deputy instrument lead of the MAVEN instrument, the Solar Wind Electron Analyzer, or SWIA, and she's done an enormous amount of work on Mars, Venus, Earth, and understanding particle and plasma transport there. So without further ado, I'd like to turn it over to Shaosui to tell us about magnetic topology at Mars and Venus.
Thanks, Shannon, for the nice introduction. So I'm actually going to go straight to the motivation because of the audience is slightly different from what I normally talk with. So the keyword of the title is magnetic topology at two planets. So you wonder, why do we study magnetic topology? On the very high level, I would say it provides insight to the planetary intrinsic magnetic fields. For example, at Mars, it helps you understand the crustal magnetism. So that helps you understand the planet evolution. And also, it helps you understand the magnetic environment at different planets. So here, at this talk, I'm going to touch on Earth, Venus, and Mars. And you can compare the different magnetic environment at these different planets. And also, sorry, I actually have been having this cough for a while. Bear with me. Also, the planet interact with the solar wind. And then that's important for understand the planetary atmosphere escape. By extension, that also helps understand the exoplanet atmosphere evolution. That's a branch of our field as well. So more specifically, at this talk, I will talk about at Mars, using magnetic topology, we review a large global dipole-like intrinsic field that contribute to Mars' hybrid magnetosphere. And then at Venus, we're gonna talk about the magnetization of the Venus ionosphere caused by the solar interaction. So there are some words that's more technical. I will explain that in later slides. So start with some basic introduction. So the most familiar one we have is Earth. Earth has magnetic dipole. To the left, it has magnetic field going out from the south to the north. But when it interacts with the solar wind plasma and magnetic field, it makes the magnetic structure way more complicated to the right. We have different plasma regimes, and then the magnetic field, the magnetic dipole gets stretched way down tail. So to the right, we see, you kind of imagine if there's a flow around put the pressure on obstacle, it will stretch the magnetic field into the anti-sunward direction. Under this, because I'm going to talk about the tail configuration, so just to orientate everybody here. So as space physics, when we talk about x direction, we normally talk about the direction from the planet to the sun. And then the z direction is normally aligned with the rotation pole. This is z will be kind of close to the Earth magnetic dipole. There's off tilt, but close enough. So this is the magnetic field in the xy plane, xz plane to the left. But to the right, if we cut through the tail, take a cut at the tail and look at the yz plane, is almost like how you have this cylinder, and it has the sunward field in the north, and then tailward field in the south. So, or if you look at the left, we have the magnetic field coming out from the planet, and here in the south, we have magnetic field coming out from the planet and point away from the sun in the south and towards sun in the north. So that's the general frame we're going to use in this talk. So that's the picture when the solar wind interact with a magnetized body with a strong intrinsic field like dipole field, Earth, Saturn, Mercury. But the picture looks very different when it interacts with an unmagnetized body. So here would be Venus, comets, and a little bit of Mars to the first order. So what happens is this planet don't have a dipole field, but it has an atmosphere. So what happens is this atmosphere will get photoionized by the solar photons. So it creates what we call ionosphere. So that's the charged part of the upper atmosphere, so make up of ions and electrons. All right. So this charged particle gonna interact with the solar magnetic field and flow, and create a similar structure we see at Earth, but in a slightly different nature. So this is what we call induced magnetosphere. If we have a prettier picture, the sun is to the, that's right, that's left. To the left, if we zoom in, we have what we call bow shock. Here, separate the upstream solar wind flow and then the downstream. And inside here, we have different plasma regimes, and then there are boundaries, separate them. So the boundary terms, I highlight them in purple. Most importantly and relevant to this talk is the induced magnetosphere. So this is a magnetic field piled up around the planet, and you can see it drape around the planet and create the two lobes in the tail direction. So that's the region we're going to talk about here. Let me know if that's a question. Feel free to interrupt, or unless we operate differently here. Just give a sense of how different in terms of the size of the magnetosphere of Earth and Mars. To the left is the Earth magnetosphere. So we see the deflection of the solar wind occurs about 10 Earth radii from Earth. To the Mars, the separation of solar wind and then the induced magnetosphere is much closer to the planet. It's about actually 1.5 radii from Mars. So the interaction is more closely and interact with the ionosphere at Mars. Also the case of Venus. Another introduction to have is there are lots of similarities between Mars and Venus in terms of like atmosphere composition, and then they both don't have a global dipole field, but there are significant differences between the two. In terms of magnetic environment, the most important thing is that Venus doesn't have magnetism, or at most a very weak one. But at Mars, we have very localized, but also very intense crustal fields. So to the right, to the left is the plot of basic, sort of like the radial component of the crustal fields. So you can kind of imagine the magnetic field going out of from one stretch to the other. So we have all these small loops on top of the planet. And then it's very messy and very localized. So when the solar wind field interact with the, say, for example, crustal fields, it creates a very dynamic magnetic connectivity. So this is what we call magnetic topology. It's defined as magnetic connectivity to the planet, like if the field line is connected to the planet on both ends, like the closed field, the red line here at the bottom panel is a closed loop. And then for the solar wind, it doesn't have any connection to the planet, is what we call draped. But these two magnetic fields, when they are oppositely orientated, it will generate a new type of topology called open field line. It's like the green line here. So what happens is when the field line is oppositely directed, it will have what we call magnetic reconnection. So it's a picture up here. So the yellow and blue line, they are in different directions. So after reconnection, you see how the magnetic field is now connected between the yellow and blue line. So that's how magnetic topology can get changed. So if at the bottom, you can imagine a closed loop reconnect with the blue draped field lines, we will end up with a field line that connect to the planet on one end and also solar wind to the other end. And also, we can also have two open field line reconnect creates a closed field line. So the magnetic topology is actually very dynamic and complicated at these planets. Just a little bit more. On the previous slide, I have, did I quote it? Yes, I quoted planet. Because for the data-derived magnetic topology, we are not defining with respect to the planet surface, but actually to the collisional atmosphere. This is because we use electron to trace the magnetic connectivity. And then these electrons, they are only free to move above collisional atmosphere. At low altitudes, they are governed by the local production, local loss. But at high altitudes, they can free travel. So we can even see electrons coming out from the atmosphere at thousands of kilometers. Yeah, so like I just said, the topology is very complex and dynamic because we have upstream IMF changing all the time. And then in the case of Mars, we have the crustal field rotates below the solar wind. So it's very dynamic. But with data, we can actually determine the magnetic topology in real time and also in 3 dimensions. So that's a pretty neat capability we have. One last introduction. This is a very long introduction, but it's necessary. For induced magnetosphere, for the Venus is more resemble what I just introduced. It has the 2 lobes formed by the IMF draping around the planet. But at Mars, because of the crustal fields, it makes the topology very complex. One more thing I need to highlight is at Venus, even though we know all the fields are draping around the planet, but if we define the topology at an altitude of, say, 200 kilometer altitude, we can actually see or differentiate if magnetic field is deep below this altitude or not. This is important because for field line gets below to the low altitudes, that's where the planetary ions are. If the field lines are connected to the ionosphere, then it can allow the ions to escape, or you can allow the solar wind particle energy to deposit into the ionosphere. So this is important information as well, even at Venus. All right. Now let's talk about how we actually do determine magnetic topology. We use the electron data. So more specifically, we look at the electron angular and energy distribution. If we can determine if the magnetic field is connected to the collisional atmosphere or ionosphere on one end, or both ends, or not at all. That defines open, closed, and draped. I'm gonna go into details how we do it. So if we look at the electron energy distribution, by that we mean to the left we have a plot of energy flux versus electron energy. So this is a measurement by MAVEN. The two lines are the measurements separated for electron traveling along magnetic field and also anti to magnetic field. So we can see there are two spectrums. They are very different. The red line is the solar wind electrons, and that means the magnetic field is connected to the solar wind on one end. And then the blue line is photoelectrons. This is electrons produced only in the daytime ionosphere when photoproduction occurs. So if we see these photoelectrons, means the magnetic field is connected to the daytime ionosphere. And how we can tell them apart? I highlighted a few features here. So there's a peak at about 20 to 30 eV here, and also a flux, sharp flux decrease at 60 eV. These are unique features in the photoelectron energy spectra. That's how we can tell the two populations apart. So to give a schematic to explain this plot, this is a typical observation for open field line observation. So we have photoelectrons streaming away from the planet, and then have solar wind precipitating. So that means the field line is connected to day's ionosphere and also solar wind at the same time. So this is a typical observation for open to day topology. But on the night side, there is no sunlight, there is no photo production. We use a different technique to infer the magnetic conductivity. We then look at the what we call pitch angle distribution, or the angular distribution of the electrons. So a plot at the bottom is the this is a pitch angle. That's the angle between the electron velocity and magnetic field. So and then the y-axis is the normalized electron fluxes. So this would be a parallel direction, and this is anti-parallel direction. So for this case, we see a strong flux depletion on one direction, and this flux depletion is caused by when the magnetic field is connected to the atmosphere, it will get absorbed by the atmosphere. So we know there's a strong electron depletion, then the magnetic field is connected to the atmosphere. And then this is what we call loss cone. If you see that in only one direction, that means the field line is connected to the atmosphere once, then that's a open field line. If it's connect on both ends, then that's a closed field lines. So by combining the electron angular and energy distribution, we can actually differentiate up to 7 subtypes of magnetic topology at Mars and Venus. So this is where we subdivide the open close further based on their foot point is on the day side or night side or both. All right, that's a long introduction. Now let's get to the results. First, at Mars, we're going to talk about how we use the magnetic topology, review the global dipole-like intrinsic field. Now we go back to the magnetosphere configuration. The top is the basic the XY plane, and then the bottom is the YZ plane you just saw at Earth. So the top we have magnetic field draping around planet at Venus, and then you can imagine in the tail we actually have the field line going sunward on the minus y side, and then tailward on the plus y side. This is different from Earth configuration, where it's more north and south separation. So between the two opposite directed magnetic lobes is separated by what we call currency. So this is where basically the magnetic field go to minimum. But at Mars, what's interesting is instead of like simple as this east and west configuration, we see a tilt of the magnetic tail lobes and also a current sheet about 45 degrees. And previous studies using MHD suggest this is a crustal field effect. That's how we started to call at Mars, instead of we have induced magnetosphere, we have a hybrid magnetosphere. That means there's contribution from both the induced IMF pi-up and also intrinsic field, the crustal fields. But for a while, we don't know how exactly how it works. This is where, when we separate where magnetic topology comes in. Right, so this is to show, again, similar to the previous slide. At Mars, if we separate the tail lobe by east IMF and west IMF, we see the current sheet is tilted, but tilted in opposite direction. What's more interesting is if we do the same mapping of the tail polarity by open topology versus draped topology. So these two are the where we combine everything but only separate the IMF. The bottom two are the draped field lines. These are unconnected, just IMF draping around the planet. For this one, we actually don't see the tilt. And then the tilt actually only shows up in the open field line topology. So in other words, if we look at the tail configuration for field line unconnected to the planet, it's very, very much induced-like. But for when we look at field lines only connect to the planet, that's where we see the tail twist. In other words, open field lines that are connected to the planet is actually the cause of tail twist. What's more interesting is if we now only look at the field line connect to the planet, that's the open field lines. So these are the two panels I just showed you. But if we combine all the IMF together, and then that's what show up to the right. And now we see a very dipole-like tail lobe. Just to remind you, for induced fields, the magnetic lobe is east and west in the east and west configuration. But for the dipole is north and south. So when we choose just get the field line only connect to the planet, we actually see a very dipole-like configuration. So our interpretation is when we averaging all the IMF condition together, the induced component in the open fields get canceled. And then we can actually see the intrinsic component of the magnetosphere, and which is very dipole-like. Maybe I'll skip this part. So the source of this dipole-like global field is crustal fields. If we look at the magnetic polarity at the close to the Mars, so this plot is the magnetic polarity at 200 to 300 kilometer altitude as a function of Mars latitude and longitude. And this is where the strong crustal fields are, where we see many slides ago. The color is blue is field line going outward, and red is inward. So if we ignore all the fine structure caused by the crustal fields, we generally see this south outward and north inward large-scale field. And then if this field reconnects with southward IMF, it will create the lobe we see. That's it. So just to combine the two together, at the low altitude, the crustal field shows south outward and north inward configuration. So we use a simple dipole schematic to show the configuration. When you reconnect with the solar wind IMF, it creates a tail lobe very much similar to Earth configuration, where is north sunward and south tailward configuration. So this is only doable when we separate the data by different kind of topology. So when we have a dipole field, how does it cause the tail twist? There's a theory back then, back in 1980s. Actually, I should say, tail twist also observed at Earth, very further down tail. So it's the theory back then is we have this two-lobe structure. When they connect to the IMF in the y direction, it adds a magnetic torque to the tail lobes. So you twisted the tails in that direction. And Mars is, I guess, is similar, but I would like to explain it as consequences of magnetic reconnection. So to the left, we have a dipole lobe, and to the right, we have an induced lobe from IMF draping. So in the quadrants with opposite color is where we have opposite IMF direction. That's where magnetic reconnection mostly likely to occur. So after reconnection, it introduced, I guess, magnetic torque to the tail configuration. That's how it twisted the tail lobe in clockwise or counterclockwise. Right. So this is just to summarize what we've seen so far. We're using topology to review dipole-like tail lobes. And when it interact with the induced component, it will cause the tail twist. Okay. One thing I want to highlight is topology is a very interesting tool that it actually can separate the intrinsic component and also the induced component of the Earth, Mars magnetosphere. So I think it's pretty well established that Mars has a hybrid magnetosphere instead of simply induced. All right, quick summarize. I guess maybe I can just skip it. One thing I should mention that before MAVEN, Mars is generally compared with Venus because both don't have a dipole field. But with more and more MAVEN research, we find Mars is actually a lot more Earth-like than previously thought. So it's actually very interesting to compare Earth, Venus, and Mars is kind of in between. I think this is one big accomplishment of the MAVEN mission. Now let's switch gear to Venus. This is where we provide the first study of magnetic topology at Venus. The study of magnetic topology at Mars has been done since 2006 by Dave Brain here a long time ago. But at Venus, because people were thinking, oh, it's just simply induced, why do we care? But by looking at the data, so this is the picture people been talking about for decades. But when we're actually looking at the data, it's not that simple. There are more complicated structure than we thought existing at the induced magnetosphere. So I'm going to start with a case study. So this is lots of panels from Venus Express. Sorry. I'm not going to introduce all this, but we are taking 2 times and look at the electron data more closely. So there's T1 and T2. I should say this is when the spacecraft is getting close to the planet, and then we are on the sunlit hemisphere. So in the T1, this is the electron energy distribution, which is the electron energy flux as a function of energy, but separated for parallel and anti-parallel direction, and also perpendicular. Let's focus on the parallel direction. We see the similar feature we see in many slides ago, the peak and then the knee here. So that's a very solid observation of photoelectrons. In the anti-parallel direction, we don't see this kind of feature. So this is a solar wind electron. As the case of Mars, so this normally means we have a field line connected to the day-side ionosphere. So that's why we have photoelectrons streaming out of planet, and also solar wind streaming in towards the planet. So this kind of configuration can happen when IMF penetrate very deep into the ionosphere. That's how you can have access to both the ionosphere and then the solar wind. But what's interesting is in time 2, this is the same data format. In the parallel direction, we still see photoelectrons. But in the anti-parallel direction, instead of saying, that's the red line here, instead of saying solar wind electrons, we actually see a spectrum very similar to photoelectrons, but at a much lower flux level. It's almost a factor of 10 depletion. So this type of observation only occur when we have a cross-terminator closed field line. So this is the like the red line here. So what happens is we have photoelectron produced on the day side. They can travel along the field line and go to the night side, and then they will lost to the atmosphere. That's what we see here. This is the flux depletion, but we still got 10% of backscatter from the atmosphere. So that's why we see a similar spectrum, but at a much reduced flux level. This is a very unexpected topology at Venus, because if you just imagine a field line just draping around the planet, it doesn't create kinks like this. So to this day, we still don't know what the cause of such a configuration. But it makes the but it means the magnetosphere at Venus is not as simple as we thought previously. And then based on some statistical study with Venus Express data, we show that this kind of configuration is not a single event. It's not some special occasion. It actually has occurrence of roughly 10%, 10 to 20% near the terminator. So it's a really great puzzle why we see this kind of configuration at Venus. And then more importantly, what happens below the exobase? From the electron data, we can only tell the connectivity. Oh, it's actually mirroring. I didn't realize that. Above the exobase. So below that, maybe it's just a field line, draped field line, but then somehow there's a kink, there's a weird current in the ionosphere, cause such a kink in the field line that there's bulge, and then goes back down, and then still going to the tailward. Maybe just simply draped, but with weird kinks in it. Or maybe it connected to the planet surface with crustal magnet field, even though it's very weak at Venus. But that's one possibility. Another possibility is maybe even it connected to the conductive core. We don't know. these are all open questions to be answered. So with the statistical analysis, we were able also to map other type of topology at Venus. So this is the occurrence rate as a function of, I should probably introduce. So the color is occurrence rate, and then the x is x and z direction. So we see the open field line occurs many in the terminator and also in the kind of in the flank where you expect this topology will happen. So that's how we were confident we are getting the right tool to determine topology. And to the right is open field line connect to the NISA. There are some misidentification, but that's not the point. All right, last but not least is the draped film lines. The current rate, you can see it basically saturates the plot. It means it is the dominant topology at Venus. It is Venus magnetosphere is many induced by nature, except for in the lower altitudes near the ionosphere. All right, to summarize the Venus part, sorry, I'm reading while I'm talking. From case study, we first discovered cross-terminator closed loop at Venus, a very surprising topology at Venus. It tells you the Venus magnetosphere is not just simply induced, at least not as simple as we previously thought. And then we have some statistical mapping of where and how frequent for each type of topology occur. Most importantly, we want to raise the open question, what are the origins of the open-closed topologies at Venus? It may just be deeply draped, have some weird current flow that cause a kink in the magnetic field. Or it may have something to do with Venus weak crustal magnetism, or it has something to do with conductive core. We don't know. But it motivates us to think about possible ways to measure the deeper magnetic fields at both Venus and Mars to understand the true topology. Whereas from electron, we can only see things happen above 200 kilometer altitudes. All right, actually it's quicker than I thought. So by conclusion, magnetic topology is a powerful tool to understand planetary intrinsic field and also induced fields, Mars and Venus. And Mars has a hybrid magnetosphere, has a contribution both from the intrinsic and induced components, and more Earth-like than previously thought. Venus is mainly dominated by draped fields, but it's also not a simple picture people been seeing or thinking about for decades. Right, and it motivates for future investigation of what is the true topology at both planets. So that's all. Thank you.
All right, we have plenty of time for questions. I'm going to get a microphone out. So give me just a moment, and then if you have any, just start to stand up or raise your hand.
Oh,
boy, what are you? Thank you.
Yeah.
Okay, questions for Shaosui. If you could just say your name and then your question, that'd be great.
Hi, that was a fantastic talk. My name is Mike Rothman. I work with Dave on the Emirates Mars mission. So I'm relatively new to magnetic fields research, but do open field lines and closed field lines evolve into one another over time? And what is that time scale for that kind of process to happen?
You mean when you change from open to close, close to open? Depends. It can. So reconnection occurs very quickly. I think we're talking about seconds, minutes, but it needs to have the right configuration environment for reconnection to occur. So there are two levels of factor to that. When it occurs, it changes very quickly, but you have to have the right condition for reconnection to occur. So that can change from measurement to measurement. Yeah.
In orbit to orbit, for sure.
Yeah.
Okay, up we go.
Hi, my name is Joe Corsi. I'm an undergrad here. I'm just curious. I don't really know much about this either. Has there been any research about the effects of like Venus's volcanism on those closed field lines that we have no clue about?
There are people trying to see, Shannon probably has more to say.
I do, as does Larry. If I could just ever so briefly point out that a recent paper by Robbie Herrick, and all very recently, this is just wild, found active volcanism using Magellan data. And this is like, meaning 30 years ago, not 30 million years ago, not 300, but I very much believe those results. And so I think if you currently believe Venus is volcanically active, which it is, then that's something to think about in terms of what we think, in terms of the interior structure and what that could mean for a magnetic field.
Yeah, I think one thing to do is to actually map the closed field in geographic coordinates, see if it's correlated with any geographic features.
Larry, do you want to add to that? I can bring this up if you'd like to. Okay, one and then two. I'm right here.
All right, so with regard to this field lines that connect the day side to the night side near the terminator, Venus is a slow rotator, and it's known that there are very fast thermospheric winds and even faster ion transport, heavy species transport from day to night.
Yeah.
I guess not having done a lot of MHD in my day, I would expect if the ions are moving from the day side to the night side and we have measurements of the velocity and they're precipitating onto the night side, that would provide a pathway for the electrons as well. But what am I missing? Is there a connection or?
So you are talking about in the collisional part of the atmosphere. So in those parts, it won't create the, so they don't normally carry magnetic field. But it is one most plausible explanation for this is you have this complex ion wind in the ionosphere. It can generate currents and it can add reshape the draping IMF to have weird kinks to create the closed loop. And that's one possible explanation. But I won't say it's those ions carry magnetic field creates the day to night. Yeah, I guess, yeah.
But certainly an interesting area, an open area of research.
Yes.
Hey, Michaela Huffman, great talk. I also work with Dave. And my question is sort of like Mike's, but less well put. So Mars obviously has a lot less atmosphere than Venus does. How does that affect this type of topology? Is there an effect?
Actually, at the thermosphere altitudes, they're actually not that different. They're probably offered by, well, the scale heights are different, but where the electron isobase are, I don't think they are offered by 50 kilometers. Yeah, to this study, they are less important, or less difference.
Hi, I'm Dave. I work with Mike and Michaela and Mike and plenty of Parker, and yeah, I work with a lot of people in this room.
Where did the question come from? Yes.
I have questions about both the Mars part and the Venus part, but I'll censor myself and just stick to Venus, and we can talk about the other parts later. And it sort of centers around the definition of open in this context. When you're using electrons, as you mentioned, you can't really tell if those field lines go all the way to the surface of the planet or just go down to the collisional part of the ionosphere and then veer off again.
Right.
And so for the Venus results, maybe a question and an idea. One question is, what is the orientation of the magnetic field at the locations you're finding these unusual structures? Is it radial or is it horizontal?
So far, I've only do the very simple study, just mapping where they are. But this is one case study. You can see the magnetic components here on this. I don't know how clear it is.
I can see, yeah.
Yeah, at least for this one, it seems like there are many in the X direction. But understandably, it's in the near the terminator.
So that would be horizontal.
Yes,
then.
yes.
Okay.
But I don't know if we go to like on the more day side part, are they still more radial versus horizontal?
Interesting. And then maybe an idea that I was mulling about is, as I was listening, is that, people have been talking since Pioneer Venus days of surface instabilities in the ionosphere, waves that steepen into vortices. And I think of the ionosphere, I'm sorry, Parker, I think of the ionosphere as cotton candy, and I think of the magnetic field lines as cooked spaghetti noodles.
Yes.
As you throw them towards the ionosphere, they're gonna drape around, but some of them will embed themselves in the cotton candy. And if that cotton candy has waves in it, I can imagine you have field lines that are embedded in two places in the ionosphere, but in the middle not, which is consistent with the topology that you're seeing.
Well, that's an interesting scenario I haven't thought of. Yeah, but I really need to do more analysis on just focus on the closed fields.
Yeah, it's interesting. Thank you.
Yeah.
I'll stop talking now.
I'm gonna go, I think we had one and then two. Okay, Robert. Just kidding, here we go.
So hi, I'm Steve Cranmer. I'm a solar person, and the question that I thought one of the Mars people was going to ask is about atmospheric escape. Right? How does the presence of these cross-terminator closed field lines that are sort of puffing up the magnetosphere of Venus at the terminator, does that enhance atmospheric escape, or does it suppress it, or could it be both?
That's a great question to ask, and we need a great mission to do the analysis. But there are ion measurements with Venus Express. I have a colleague. We wanted to do analysis on possible ion escape on different topologies, but it's just future work. Sorry.
Hello.
Oh, sorry.
So Judith and I were wondering, we didn't want to be left out. You see the closed field line, the deviation from an induced field at Venus like 10% of the time. Do you, are there any conditions at Mars where you see the crustal fields obscured by, any conditions? Are there conditions where sometimes you won't see the contribution from the crustal field?
Sorry, you mean? Oh, actually, Mars is interesting that I think there are closed loop connecting very distant crustal patches. So you can even, I think, we can see closed loop on like solar angle 120. So that means one end has to be on the day side, and the other end goes down to 120 solar angle degrees. So it's crossing many tens of degree of we can have very long closed loop at Mars.
So it's a lot larger in scale, but does it ever disappear empirically?
Oh, it changes all the time because you have reconnection occurs, so it can be closed at one point, it can be open, it can be deeply draped. It's a very dynamic thing. Mhm. Yep. Yeah, actually, one point I skipped was it's exactly what Shannon said. We will see more open field line during software IMF. So that's more likely to occur during ICMEs. So it has implication for early Mars condition, because that's where we have lots of ICMEs. So you kind of expect the system to be more open at early Mars than the present days.
So I'm Nick Schneider, and my question is predictably about aurora. And we know that magnetic field topology is an organizing scheme for aurora on Mars, both crustal fields and cross-terminator closed field loops. And there are two spacecraft orbiting Mars and scrutinizing the planet for aurora, but there are 0 doing so around Venus now. So you have the chance, with your understanding of topology there, to predict what aurora might be happening there with your understanding of the field lines, which can both enhance precipitation or prevent it. And show a diagram of Venus and just make stuff up so that we can just imagine this.
You mean this one or this one?
Yeah, that one. That's good.
Yeah.
Where should we look?
Actually, so this is open to 9. This is where I expect we see the precipitation occur.
The aurora already seen for by Pioneer Venus and ground-based observations at Venus, or?
Shannon can correct me if I'm wrong, but I think there are 2 types of aurora observed at Venus. One is from PVO, another is from Hubble, maybe, the Earth-based
Apache Point Observatory.
Yeah. So I think they're talking about the SEP aurora, just like Mars, but there are patchy ones observed. I think some of the patchiness might come from topology.
Right, and that would be lower energy electrons that would be controlled.
Actually, let me say, I don't see a reason why we don't see what we see at Mars, at Venus, if we have the same instrumentation. I don't think there's a reason not to see it, especially with EMUs. We can see emission from just the low energy electron impact. We just need the right measurement to see it.
So I will take host, So you've got 2 missions. Well, you've got one mission coming up that we know. It's in phase D. That's Escapade. And then you've got the dream mission to Venus coming.
I know.
Because we're going to send one. So could you comment on what are your dream measurements from Escapade? What would you most like to see? And then what would you most like to see at Venus if you could have any measurement you wanted?
In terms of topology, or just, with
dealer's choice.
I think with Escapade, because we have 2 spacecraft, I think we can do a lot more with temporal variation than MAVEN. And then also, I guess, spatial, some of the spatial difference too, but more temporal.
Meaning like how fast some of those the topology changes. I
exactly.
think to one of the questions up here.
Yes.
Okay, so
yes.
We could get better definition there.
Yes. Yeah, and also some process might be easier to understand if we have 2-point measurements than single one. For Venus, I mean, even if we just have MAVEN going into Venus, I think we're gonna see lots of new stuff, revising our understanding of Venus, just as MAVEN did with Mars. Yeah, I don't expect anything less than that.
And then just last question. You said early on in your intro slides that you believe Venus is, again, weakly or maybe magnetized, but can you comment on any other signs? What are the other things we would look for if we really wanted to understand magnetism at Venus, right? So we've typically said it's unmagnetized completely. And now obviously some of the results you're showing indicate that the jury's still out at the very least. Are there any other things you would look for?
I'm less familiar with the crustal magnetism story of it, but to understand it, we just need low altitude magnetic field measurements, right?
Agreed.
Yeah. And I think there's some effort to trying to see if there's some magnetic feature, like more radial over some particular region of Venus, that might mean there's crustal field there that somehow we can see at hundreds of kilometer altitude. But it'd be much easier. We actually fly to low altitudes and just measure it.
Great idea. We should go.
Right.
Like a balloon, for example.
Exactly.
That's one way.
Yep. I totally agree.
Any other questions for Shaosui? I'm glad you ended early. We were actually, we've had lots of interest. We do have another. Hang on.
Oh.
Would you be able to pull up the Mars crustal field map?
Sure.
Yeah, that's perfect.
This one? Sorry, this one?
That one, yeah.
Okay.
I was curious why the crustal fields appear to be so offset. Like it seems funky that the red box extends all the way down to what, 20 south latitude?
Right.
Versus the blue box.
Right.
Do we know why the crustal fields formed that way? Is it like a consequence of the dynamo, or?
If I know, that would be a Science Nature paper.
Okay.
No, I'm just kidding. It is true that it's still an unknown question why the crustal field is this way. But it probably has something to do with the strongest crustal field is kind of in the south. So that's a hint to its formation magnetism. But the exact reason is still largely unknown. What's interesting, I didn't want to go into too detail of this, lots of details, is when we see crustal fields like this, we'll think, oh, they are randomly orientated, kind of like scattered around. But somehow, even you just look at this equator belt, you can see also this kind of blue in the south and red in the north. I feel like the crustal field we see so far is more organized than we previously, just than randomly organized. I think it's more organized than just randomly oriented.
And for many of our geology colleagues, they might note that the northern lowlands and the southern highlands adds into this really interesting asymmetry between the north and the south, but they don't actually perfectly map either. So that sort of adds to thinking about interiors, thinking about volcanism and resurfacing and that Curie point and that temperature, right? And what gets locked in and what doesn't and when.
Yeah, even why we have these what we call arcades in the south is still a very big unknown question on Mars.
We have 1 minute left, so I'm very glad we got so much Q&A time. Any other final questions for Shaosui? All right, let's give our speaker a big round of applause.
Thank you.
And as a reminder, next week is canceled. I hope you're going to the eclipse, but if not, get excited anyway. It will be partial eclipse, and that will be very exciting. So we will see you in 2 weeks.
Hi. Thank you for coming. Sorry.
I am going to unmic you.
Sorry.
No, you learn once the hard way.